Yeah, I'm master's.
I really liked doing the science degree because it was a lot more kind of modeling about things.
Yeah, that's nice. Okay, we need to get started. All right, good afternoon, everyone. Let's get started. First thing we are going to go over is one of our policies, and today that's drop or withdrawal policy, which says that students may drop a course within the first 2 weeks of a given semester without any penalties. Student may officially withdraw from a class or all classes after the drop deadline through the midpoint of a course. W grade is recorded on the transcript and appropriate tuition fees are addressed. The grade W is not used in calculating the student's GPA. And for deadlines to withdraw from full term, first and second session classes, see the use academic calendar. I do want to mention something else that's related to this withdrawal in the first 2 weeks without any penalty. I decided that I will require some of the homework assignments to actually write some Python code, specifically to use some Python libraries. And this shouldn't be anything too difficult or super complex, but I think it's important for you to finish data mining knowing about this library, and you're going to go through some basic usage of them. So this might concern you. I don't know if you feel like this might be too hard. You might consider this option, but I really believe that this shouldn't be too complicated, but you need to decide for yourself. So that's one change in the syllabus that I'll make. Another change is regarding communication. So what became apparent once we have published the first homework is that there is a lot of questions, and a lot of questions go straight to my inbox where you would like to hear my opinion compared to the TA's opinion. And that's really hard for me because I have to do research, I have to give service to the university, I need to give service to the research community and so on. So your messages get mixed up with all these other messages and I can't prioritize your messages over the other. So what we are going to do is switch to Piazza that has one useful feature, and that's where I can endorse message. So if you see that I have endorsed TA's message, you can just conclude that I would tell you the same thing, and there is no need for reaching out to me directly. Of course, there will always be personal circumstances where you will reach out to me directly, but Piazza has all the options for you to reach out to instructor directly, indirectly, make things private, hidden. So I think it's going to be a little bit easier for me and therefore better for you because you will get my response in a timely manner. Okay, so these are two things that are going to happen. They are not implemented yet, and once we have implemented them, we will announce them on Canvas. Okay, so I won't go into details of some of the stuff that were unclear in homework yet, because we have those two in the late policy. I say you get 2 free passes for being late. So some of the people might not have submitted their solutions yet, and it wouldn't be fair to put people who have submitted them that I now discuss solutions. So we are going to do that on Monday. But I want to go over some of the stuff that were unclear that I didn't explain to you well enough last time. Are there any questions about the changes in the syllabus and what else did I say about Piazza? No. Okay. Oh, no. All righty. Then let me navigate this thing. Okay. All righty. Here we are going to. So these are the lecture notes from the last time. And there were at least few things that were unclear. It was unclear how to use multiplicative hashing for strings, and basically we'll need to convert strings to integers. And there are ways to do that. I won't go into them, but that's what you would do. Then another thing that I brought up is that there is this rule of thumb that you can use for the number of steps that comes from this equation. And righteously, there was a question of where this came from, and I didn't provide an answer to that. So I added to the notes how do you come to this rule of thumb probability. From the equation we have derived when we assumed independence. So from this equation here, okay, we have this equation, and you can use some steps to get to that approximation. More specifically, so this is that equation that I have just highlighted. I think you would need to use is binomial theorem and realize that this term here, you can expand using binomial theorem. And you would use the fact that the powers of 2 and higher will be very small for a very small x. Or in other words, here we have excuse me. Okay. Just a moment, I have a little iPad difficulty here. All right, so if n is large, then 1 over n will be small, right? And if when 1n over n is small, then power of 2 and higher will be even smaller. So you can kind of say that this thing here, you can approximate with this thing because x on power 2 and so on will be very small. And when you combine all of that together, you will get this formula here. And then you will use the fact that you can also approximate k choose 2 with the same principle. So here we have very large k on power 2 is way bigger than just k, and therefore you can approximate it with just k to the power of 2 over 2. And when you combine all of this together, you will get that formula. Yep, go ahead.
That's kind of a Taylor series approximation.
Yeah.
Okay, so that's okay.
Yeah. All right, so that was unclear last time. If you're now a little bit fuzzy of what's going on, just open the notes on the web page and everything will be clearer. And the last thing, I believe, two things that weren't clear. So here on this harmonic number, I was confused and I didn't set the range for our I correctly. So now there is that, and it's correctly written in your notes. And there was a question about can you give me the probability, given k purchases, can you give me the probability I will see all the toys? That's something I didn't know how to derive last time. And actually that turns out to be a well-studied problem. The derivations from the formula we have seen are not trivial. They are possible, but it takes a little bit of effort to do it. And if you actually look at real solution in the math to that question, I recommend looking at this Stack Exchange post. There is one way to do it if you know what Stirling numbers are. So you could use that to get that probability. And this is something I will share on Canvas or Piazza. Depends whether we make Piazza available here. So I won't go over all of this, but just know that it exists. And you do need to know a little bit more math techniques that we will cover here to get to it. Okay, so that's all about the previous lecture, and these, as I said, these notes with these corrections are available on the website. I'm trying to close this there, which is not possible. Okay. All right, and before we go into the new lecture, I want to remind you that the deadline for the project proposals is coming up, and to submit the project proposal, you need to form a team. So we have set up a deadline for you to set up teams, I believe on Thursday at
6
tomorrow at 6 p.m. So if you don't do it by then, we will just randomly assign you to groups. And as I said in the first lecture, you have to have a very compelling reason to be a team of one. So you must be in ideally group of 3, not more. I have also brought some posters here such that you can see what kind of projects are, we expect for this kind of course. But in general, for every class, I would really ask you to not stay outside of the class, but rather meet us at that room we have booked for office hours. I know there is, you just want to ask me a quick question and go home, but it makes it a bit hard for us to answer all the questions. And there are also our TAs who can help me to answer your questions. And if you are in a crowd, you don't see them. So please, unless you really, really hurry, please come to that room instead of waiting for us outside. So I said that because I will bring the posters with me into the room, and you can come there and look at them at an easier pace. Okay, and yeah, the last thing is that now the new homework is released, and for this homework you have 2 weeks, and we will try to keep that rhythm that we release homeworks 2 weeks in advance. Sometimes, depending on my schedule, for example, if I travel, there might be a small delay, so it's not fixed in stone that it was always going to be 2 weeks in advance, but we will try to do it like that. All right, so now we can finally go into our new lecture. Yes, please.
About by what lecture would you expect us to have learned all that we need to do to start hosting?
Oh, that's a good question. So today you will hear everything you need for the first assignment. So first, problem in the assignment. I believe that already in this next lecture we will cover. So next 2 lectures will cover the rest for sure. Yeah, so right after today's lecture, you can start working on the first problem. Excuse me, I need to navigate between iPad and laptop, which is sometimes a little bit cumbersome. All right, so what we're going to do today, and it's going to span the next 3 lectures, is a fundamental problem of data mining, and that's finding similar items or examining similar items in your data. So let's write that down. So fundamental problem is items. Okay, and some examples of that. Some examples of that are, for example, detecting plagiarism. Like you might have, as I said, I'm a part of the organization committee for a conference as we get a ton of papers, and now we need to see, are those papers in a way too similar to some existing paper that already exists in the scientific community? And there are so many papers, so you have like a huge pool of papers. So plagiarism is one of them. Then we might have, on the web, we know that different pages have different mirrors to share the loads. So we might want to also identify that these are similar. Or maybe we have news articles, how one news outlet writes the first article and then everyone else takes the bits and pieces and reframes it a little bit, especially if they are translating it to another language. So you might also want to know, okay, what are articles from the same source? So these are just some examples, and I bet you can think of many others. It's really like a really prevalent problem. And you might have like an idea to, okay, I know how to go about this. I will just compare every pair, right? And I will see whether 2 pairs are too similar, and if they are, if 2 papers are too similar, I will say, well, this paper plagiarized this other one that was published before. So that could be your totally legit idea. And the problem that that occurs is when we deal with the big data, which is the thing we are dealing with when we deal with data mining. So if you have, let's say, number of items equals to 1 million, then let's call this n. Then in the last lecture, we have said, okay, then we have n choose 2 pairs. So we have n times n minus 1 over 2 pairs, which is then for n of 1 million, that's already 5 times 10 to the power of 11 pairs. And basically, if you would compare if you would compare 10 to the power of 6 pairs in a second, comparing this many pairs would take 5 days. And if you had 10 million items, this would take 1 year. So obviously, this is not this obvious thing to do is not what we would do when we are dealing with the big data. So we cannot do this because it's too slow. Because we have this problem, right? And what the point of these 3 lectures is going to be is to see how we can do this more efficiently, right? How we can actually compare pairs of items such that we don't lose so many times and have actually useful applications. And the actual solution we are going to work to is called locality sensitive hashing, where we will actually deploy those hashing functions we have learned last time. So it's very nice when we use something in stats that we are going to actually apply for a very, very real problem in the world. All right, and the idea of locality sensitive hashing that we are not going to go into details today, neither next time, but in 1 week, is that, okay, you have two documents. You are going to just use a bunch of hash functions to hash them, many for one and the other. And then you're going to say, well, my 2 documents D1 and D2 are similar if they hash, if they have some hash for some of these hash functions I have used. And if there isn't such a hash function, then you can conclude that they are dissimilar. And this will be way faster. So basically you are randomly bucketing them, and if they do not end up in the same place, you can say they are dissimilar. And since we have, like in your homework and the last time, you realized, okay, I need less trials than there are actual items to achieve that collision. Okay, so this is what we are going to work to this locality sensitive hashing, but we will need few techniques before we can actually be able to do that. So our roadmap to Sage will look like this. Today, we are going to go over how to represent documents, textual documents, with sets. So here we have 2 documents, and each one of them will be represented with some sets. And then we are going to use set similarity to compare them. So specifically Jaccard similarity. And then we can say they are similar or dissimilar. And this is what we are going to talk about today. How to go from text to the sets, and how to use Jaccard similarity to compare these sets that represent text. And then next Monday, we are going to talk about the problem where this set here can actually be large. And then you run into issues again. So we are going to use a technique called min hashing, where we are going to represent this with smaller sets and approximate Jaccard similarity. That's what we are going to do next time. And then on Wednesday, we are going to combine the idea of LSH with what we get from min hashing. Okay. So this is how we are going to go about doing this locality sensitive hashing. So just put your mindset into, okay, we have 3 steps toward this, and each lecture is bringing us there. All right, so as I said, today we are going to go from documents to sets. And since I will need textual example, I will use some slides here to go over this bit. Okay. All right, so here we will have a running examples of these 4 sentences. I am Sam, Sam I am. I do not like green eggs and ham, and I do not like them, Sam I am. It's a little bit disturbing to read it. Yeah. Okay, so the first thing you can do is a very common procedure. You can define your vocabulary. You basically use all the words that exist in these 4 sentences, and you do not duplicate them. You basically deduplicate. If word am had appeared twice, you will just put it in here once, and then each word will be represented with 1 integer. So usually we put them in the just alphabetical order and numerate them. So there isn't any kind of hashing or anything here, as this might be a little bit confusing single of that. This is just making a list of words and giving them integers. And then what you can do, and this is called bag of words, is produce the vector that at each position is putting the count of the corresponding word in the vocabulary that appear in that sentence. So, for example, word am had actually appeared once in this sentence, and you are going to put it once here. Excuse me, you will put the number 1 here. Then and do eggs, green, ham do not appear in first sentence, so you will put all zeros. Then you come to word I, it occurs once, you will put number 1, and so on. And you can do that for each one of these sentences. And here is the only occurrence of a word count being twice, more than 1. So these are bag of words, super simple way of representing words. But there is an issue with this approach. And does anyone identify what's wrong here, or what could be better?
Word order is not considered.
Exactly. So we have 2 sentences here, I am Sam, and funkier version of it, Sam I am. And we do not capture that with this bag of word representations. They are exactly the same. So basically, we kind of completely discarded syntactic information about this sentence. And that's not great. For example, if you are working with these vectors to decide whether a text is formal or not, you would not have a great representation, because although this second sentence is way more informal, it would not be captured with this vector. So we want to do something a little bit smarter, and we use what we call k-grams. And specifically here, we will focus on k-grams with words. So what are k-grams? So basically you take from each one of these sentences a sequence of k words. And if we have k equals to 1, that means give me single words in this collection of sentences. So we have I am Sam and so on. However, we could have requested 2 grams, which would mean to take a sequence of 2 words. So we would have I am Sam, 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 I do not, and so on. And in NLP, and I think more broadly, when we have 1 grams, we will call them unigrams. When we have 2 grams, we will call them bigrams. 3 grams are trigrams. And then from 4, we just say 4 grams and so on. So if you look for, if you encounter these words, they are super standard, and I encourage you to use, actually say unigram. It sounds more as if you know what you're talking about. Okay, so we have these k-grams, and okay, what might happen here is that we make small spelling mistakes, which are super common when we have, textual data on the internet that we are dealing with when we deal with data mining. So we might say something like, this movie is awesome, and then someone might slightly misspell it. This movie is awesome, and then W, because W is very close to E in the keyboard. And if you do these kinds of k-grams with words, this will be, the main word will not be captured, basically. The word awesome will be very different from what we have in the vocabulary. So another idea you can exploit are k-grams with characters, where you are looking for a sequence of k characters. So for example, if we have k equal 3, then we would have I, A, M as one trigram here, and so on. I won't read them all aloud. So they're quite useful for checking these kinds of spelling errors. They're also very useful in morphologically rich languages. Yeah, go ahead.
So this does not consider like settings.
That's a great question. So the way that that here we are doing it, we have listed all of them as if they are part of the same document. However, if you consider them to be like I am Sam is one document and Sam I am is the second document, you will look for their k-grams separately. And then you will do some kind of similarity between these two sets of k-grams from document 1 and document 2. Yeah, that's a great question. So not to confuse you, this is just an example where we are kind of, we consider this to be one document, and then we calculate k-grams from it. Yeah.
Does the ordering of the k-grams matter?
What kind of ordering?
Like, I mean, if you like mix the words up, or like if the words that are next to each other, yes.
So if you mix words together and you use unigrams, it won't matter. But if you are looking at bigrams and you mix words because you're looking at the sequence, then it will matter. And that's the point, right? That you capture that difference in the ways things come. Okay. So these are programs and so on. And this is the way we are going to represent our text today. This is the set representation that I have mentioned before. And then we are going to do something with this set representation. Okay, before I move forward, I also wanted to highlight that you might be aware of some distributional or dense vector representation of words, and you might be like, are you cheating us? Like, I know we are using something fancier here. And you would be right that these days in NLP, we represent words with vectors that have continuous values, not those vectors, bag of words vectors. We have, integers that are counts in their values. And next time, once we are over with LSH, I will go over these vector representations. However, I want to emphasize that these kinds of sets of n-grams or k-grams are very useful still to this day, because there are a lot of pre-processing we do with text. For example, we want to know which language the text is written in, and it's way better to use this kind of lightweight k-grams approaches than trying to train, let's say, a neural network to predict whether you are going to tell you which language the text is written in. Or you might be aware of something called large language models. And for them as well, when we scrape the text, we use this k-gram. So there is a lot of applications of these sets, despite these more fancier versions existing right now. So this is still very much important. Okay, any questions about k-grams?
Can you
use a background with character only for a part of the word, for instead that you're wanting to check all the verb form of life, for example, like being like all those can do that.
So you would start with a document, and document would have an actual execution of text, right? So if a word like appears there, you are using trigrams, you will have the, basically you will have, excuse me, from word like, let's say you will have I like this, and then ignore what happens from here. We will have L-I-K-I-K-E, and so on. But if you didn't have word, so let's say that word liking doesn't appear in this text, actually, you wouldn't capture the engrams character engrams that are specific to that word. So it has to appear in the text for you to actually put it in the set of k-grams. Also, I will use k-grams and engrams interchangeably, so don't let that confuse you. I use engrams, but in the lecture from previous years, there was k-grams to use. It doesn't matter. You can use m-grams or l-grams, whatever, but k and n are more frequent, and I am used to engrams, so engrams will slip. So don't let that confuse you. That's the same thing. Yeah.
Is that a blank space in the word?
Yeah, that's a great question. So it is a modeling choice. And actually, yeah, thanks for reminding me. I should have told you that we have made several modeling choices when we were constructing these things before. Again, need to navigate between those things. Okay, here we go. So let's see. Let's go all the way back here. So here, for example, we excluded punctuation, periods and commas from our vocabulary. Should we have done that? It depends. It really depends on your task. So, for example, the use of punctuation is really important for news articles, and you probably want to model it. If you're working with tweets, it's less important, and you just might be like, oh, let's discard them. One thing I didn't mention is what goes into vocabulary. Here, I have included everything except punctuation and periods. But very often when we work with these things, we would collect all of the words, collect their frequency in some corpora you are working with, and then cut the vocabulary depending on some count of the word. So we'll say the word must appear at least 3 times to be included in the vocabulary, because these other ones are so weird that we won't get anything from them. So that's something we have done here. Then you mentioned the white space. So here we have discarded them. For example, in homework, I have said include white space in your k-grams. So you might see both of these versions. I think that's all that we have. Okay, another one is that we lowercase the text here, and it's another decision you made. Are you going to lowercase it or not? If you have a lot of proper nouns, you should probably not lowercase them, because that gives you information that we know that a lot of names are written by capitalizing the first letter, so you don't want to lose that information. So yeah, a lot of modeling decision one always has to make when dealing with text computationally. Okay, let's move on. Oh, I keep forgetting I need to go to the next page on iPad, not on laptop. All right, so we have now represented our documents with sets here, right? And now the goal of today's lecture is to define similarity between sets, such that we can say these two textual documents are dissimilar or dissimilar. So, okay, I could write what I just said, but I will just hope you remember that. And one concrete metric we are going, one concrete similarity measure we are going to use is called Jaccard similarities. So let's see how it works on a toy example that doesn't involve any words, but some integers instead. Okay, let's have A be 1, 0, 1, 2, 5, 6. And let's say B equals 0, 2, 3, 5, 7, 9. Okay, then Jaccard similarity has the following formula, always not just for this specific example. It is equal to the size of the intersection of these two sets divided by their size of their union. So basically you're saying these two sets are as similar as we are going to measure how similar they are based on how much shared items they have relative to all the items that exist when we collect all the items from set 1 and set 2. So here, maybe you remember or not, the set operations. So I will go over that. So we have set B, have set A. Wow, this is really funky how I illustrated it, but this is intersection, right? So this is A intersection B, and then no, A in union B. It's going to be everything that's in both sets. That's A union B. Okay. So I guess this should be pretty intuitive, right? There isn't much to it. And then if we plug in our concrete values for A and B, let's see what we get. So, all right, can you shout at me what is in intersection of A and B? 0. Oh, we heard two different numbers. What's the next one? I will pretend you all said 2. Let's tell them in the order from smallest to largest. And then the last one. Someone is impatient. Okay, then what's in the union of these two things? 0. You sound like a bad choir. Yeah. And then we take the cardinality of each one of these things. So in the first one, we have 3. In the union, we have 1, 2, 3, 4, 5, 6, 7, 8. All right, and that's, I believe, approximately 0.375. Okay, and then if we imagine for a moment these A and B's are representations of two documents, then we would use Jaccard similarity like this, and we would say that they are this similar. Okay, and maybe if it's not obvious, the max here that we can achieve is 1, right? Then everything that's in the intersection is actually in the union. Okay, questions about this? Okay, so this is not the only measure we can use, and there is actually a whole family of them. So we can use a generalization of set similarities. There is a formula for this. All right, so formula goes like this. We have parameters x, I, z, and z prime, and they are all larger or equal to 0. And when we take similarity of A and B, it is equal to x times cardinality of the intersection plus y times A union B, but then we take the complement of this thing. So what is that? Again, we have our universe of all possible things that could ever be put in any set in our world. We have set A. We have set B. And imagine where is the union. Now we take everything in the universe that's not in the union. And that would be something like this. So everything that's outside of union is the complement of the union. All right. Then we have another set operation that we haven't seen before. This is cardinality of symmetric difference. Okay. Again, we have A, B, which color? Okay. So difference of A and B, it's not this, like you can't swap A and B here. So everything that's in A and that's not in B is here, and everything that's in B and is not in A is here. And this is the symmetric difference of A and B. Okay, so basically you discard from the union what's in the intersection. Okay, and the denominator looks very similar. But here in front of the symmetric distance, you have A prime. So the only difference is this this guy here. Okay, so this is a formula you can use to actually get your Jaccard similarity. So we are going to go over 5 examples of concrete formula that you get when you plug in parameters x, y, z, and z prime. Okay, so first one is Jaccard similarity between A and B, which is equal to that generalized formula where we have parameters 1, 0, 0, and 1. So this is x and this is z prime. So we have x time, excuse me, I won't write it. So here 1 time A intersection B, y and z are 0, so nothing else goes above. And then again, we have 1 times A intersection B plus 1 time A symmetric difference B. Now you might be looking at this and telling me, well, this is different formula here than you are giving me right here. But it's basically the same thing, because here we have intersection, and then here we have everything that's in union except intersection. So together we get the entire union, right? So we get A intersection B over A union B. Is this clear? It just requires that you visualize those set operations. All right, that's one example. Then we have Hamming similarity, which you might have heard of if you know Hamming distance. They are related, and we are going to have a whole lecture on distances, so I won't go into similarity versus difference thing right now. We will just focus on the similarities. So Hamming similarity, again, we can get it from that generalized formula if we put values of our parameters to be 1, 1, 0, 1. Okay, let's do that. We will have 1 times A intersection B plus 1 times A union B complement, or Z is 0, so nothing else. And then we have 1 times A intersection B plus 1 times A union B complement plus 1 times A symmetric difference B. Okay, and we won't use it in this ugly form here. We'll do something a little bit nicer. So let's see what we can do here. We can first observe what this thing above is actually is. So we have 2 sets. Okay, I will stop coloring them because that's taking a lot of time. So we have here intersection, and then we said, okay, we have A union B complement is everything outside union here. So a different way of saying this, okay, we included everything in the universe that's not in the symmetric difference, right? The only thing that's kind of excluded here is the symmetric difference. And let's say that your universe can have at most n examples. So you would have, excuse me, you would have n minus cardinality of symmetric difference. Okay, and then below we would have three things again. We would have A intersection B, then we would have everything outside of union, and we would have symmetric difference. Which basically means that we have included everything, right? When you combine these three things together, you have included everything, every possibility. So what's going to be in denominator is just the size of your universe. And this is the standard way of writing Hemming's similarity. Actually, you would do this, which is, yeah, very similar. Yeah, so this is the last thing I have written. This is what you are going to see as Hemming similarity. But, you know, it's useful to know that it comes from this generalized set equation, and that you just put certain parameters and do these kinds of set operations to get to this final solution. All right. Any questions so far? Okay. Can you follow? Oops, excuse me.
Sorry, can you just go back to the generalized equation?
Mm-hmm. Yeah. Oh, yeah, I guess it would be useful if it's always up there. Okay. Let me know when you write it down. Yep, good. Yep, go ahead.
So why would we use this over just the basic formula?
Oh, they're useful in different situations. So one, like the different way of asking what you're asking me right now is which one should I choose? And again, this is a modeling decision. So there are some, you can connect, for example, one of them to F1 score, and you can say, okay, this is not great if you are excluding false positives and stuff like that. So they are different, and depending on your application, one might be more useful than the other. And again, if you are deriving some mathematical, conclusion, you might use one over the other to get to that. So under one similarity, you might get what you need.
So the type of the similarity in this case is defined by X, Y, Z, and Z prime.
Yeah, exactly. And when I'm writing these forms here, you can see I'm putting the X, Y, Z, Z prime as a subscript for S. Yeah. Yeah, so in the lecture, in homework, we focus on Jaccard similarity, but these other ones are useful to know. It's not like they're less worthy. Yeah, go ahead.
For the general formula, why is that problem in the Z prime at the bottom? Why is it Z prime not on the top and bottom?
Okay, to get all these formulas, you can imagine going about this other way around. Imagine like mathematicians in the world have proposed all kinds of formulas, and then someone has said, oh, guys, you can write all of them in using one way, like one formulation, and you need these parameters to tweak them. So basically, there is not much to it. You need these two parameters to get all these other formulas that we are deriving. Yeah. And maybe someone, who had derived these generalized formulas had seen a principal way of doing it. So that, I don't know, maybe there is more to it. Right, let's continue with our examples. The next one is called Andberg. AB. So here we'll have similarity of 1, 0, 0, 2, AB. Plugging them into our general formula will give us 1 times A intersection B, 1 times A intersection B, then 0, 0, so nothing above, and then finally I symmetric difference B. And again, we'll need to do some set operations to get to the actual formulation that's standard for this similarity. So what we are going to do is basically, oh no, that doesn't exist with sets. We're going to, here we have 2 times A intersection B. Let's just write them in a more silly way, just write them twice. And then let's examine what these 2 things give us. We have intersection and we have symmetric difference. So this means we have covered the union, right? And we are going to just write it like that. A union B plus a symmetric similarity of B. And here we had a intersection B. Okay. So that's the standard form for this one. And we have 2 more. You're really enjoying this.
Can't write fast enough.
Yeah, I will try. Okay, let me try my best speed writing I can do. Okay, we have Regis Tanimoto, have RT AB equals to S1102 of AB, which equals to A intersection B plus A union B complement plus A intersection B plus A union B complement again plus 2 times A symmetric B. And then again, looking at what these things are, you would get the cardinality of the whole thing, a symmetric difference minus, plus a B. All right, so that's the final one. And okay, I will then maybe go quickly through, not go over all the set operations. And we have the final one. You made it. This one, it was proposed by, I believe, biologist Sorensen, but then actually written up by Dice. So it's usually known under Dice's name. S2001 AB. All right. If you think I'm enjoying this. Okay, I skipped over all the different ways to combine these sets to kind of speed things up. Yep, go ahead.
I was like put like S1112 came out myself. Like what the difference is?
Yeah, I mean,
It's combination like more numbers.
yeah, again, try to think about them coming first before the generalization. So all of these things come with certain nice things that enable you to evaluate other things and measure the similarity and so on and have different applications. Making a connection of where the similarity would be useful and then, you know, writing it up. Okay, maybe now it's obvious, but it wasn't back then. So yeah, if you now choose something else for your parameters and name it after yourself, probably you won't get enough credit unless that's very useful for something and there doesn't exist similarity metric that was that for that specific purpose, it doesn't just exist. Yeah.
Will we discuss each of these and where they're useful for different things?
No. Yeah. Not today. I didn't plan it to go over all of these things. But yeah, I can see why would you like to know more about this information? So yeah, the answer is no, but I can definitely share on Piazza once we activated different resources where you can read more about these things.
I guess I'm just not sure why I would pick one of these over another.
Yeah, I can see that. Yeah, let me then just share more materials and that will include this information. Yes. Okay, but your question kind of gets to the one point, which is, how do we choose these things? And for basically all of them are a reasonable choice. No one would be surprised that you use them if you are calculating similarities of the sets, and then which one you have to choose. Maybe there are, as I kind of hinted with my answer. So here we are the question is which one to choose. So if you're working on a problem and other people have discovered that for your specific problem, one of these similarity measures is better than the others, you would just go along with that one because someone already made the effort to discover that it's really good for your use case. So this is generally the case. You would not only for set similarities, for every modeling decision you do, you are going to check what prior work has done. And you can tell I'm an academic because I use prior, meaning there are prior publications. In industry setting, there is always going to be a colleague that has worked on a similar problem that you can get an input from of what would be a usable thing here based on their prior experience. And then another thing we use, especially in like machine learning, is we typically have train and development and test splits of our data. So you could try all of these metrics on your development set. So 1, 2, 5, excuse me. And then you'll find out, let's say that the 5th one is the best on the dev set, then you would report it on your test set, just the 5th similarity. And you would report that when I use this similarity metric, I get these test results. I don't know what exactly your task would be, but that's how you got about it. Okay. All right. Okay, so I will go back to slides and we'll go over how to use Jaccard similarity there. And then I actually will ask you to calculate something for me. Okay. All right. Okay, going back to the example with our SAM, let's try to apply what we have now seen for Jaccard similarity to the concrete example with actual text. So what we would do is let's say we choose words and we choose K of size 2. And again, this is another modeling decision, whether you want to choose words or characters and what's the size of K depends on your application. So if you have very long text, you might use larger values of K and smaller otherwise. If you have lots of very informal text, where possibility of spelling mistakes is very high, you might want to use characters and so on.
Oh, I have a question. So for foreign language, where do if you have like a different conjugation of a verb, where you have a different declension of a noun, are they taught by the same or
if you are using unigrams on a word level, you just capture the form, the whole form of the word. So let's say unlikely, you would just consider word unlikely. If you are using characters, then you will, let's say you are using characters of with K equals 2, you would capture the prefix un and then the rest of them, which will be very useful. Sorry, second,
Like E and H would be classified differently.
eat and ate.
I mean,
Yeah,
technically,
yeah.
the word is-
I mean, there is no classification here. You're just splitting your text into a set, right? So you're not classifying them. You're just deciding on how to split the text.
Okay.
So yes, if you are just using words, they are going to be split into individual words, and of course, these are completely different words, so they won't share anything together. But specifically, when we work with NLP models these days, we use something which we call subword tokenization, which is somewhere in between words and the characters. So these are very frequent subwords. So I gave you an example of unlikely. So here you have un prefix that typically indicates an antonym. Then you have like, which is an actual verb. And you can kind of capture with the last character that you are talking about, I believe, proverb. So in actual NLP, we would use this subword tokenizations when you're trying to model something, like build a classifier on top of it. Yeah, and if you use tokenizers that are available for you in libraries, such as, let's say, Hugging Face, you just use that tokenizer and you say tokenizer dot tokenize, and then you give that text and it will split this text for you in those subtokens. Yeah, and you wouldn't know, I would believe, like it wouldn't be like the easiest thing, like it wouldn't be as easy for you to provide these meaningful subwords as it is to split text in these things. Okay. Let's move on. So what we are going to do when we are calculating Jaccard similarity between different documents, we are going to represent each document with these k-grams. Reminder, we have chosen words with k equals to bigrams. So for sentence I'm Sam, we'll have I am Sam. For Sam I am, I will have Sam I and I am, and so on for the rest of the sentences. So basically, here we don't have brackets, but these are the items of the set we have talked about. All right, this is the formula for Jaccard similarity. And then for the first sentence, we would have that I am are the shared bigrams. So we have one in our intersection, and there are three distinct bigrams here: I am Sam, and Sam I. And remember this, you need to look at it when you are doing the union, you're looking at distinct things. So there are no duplicates when we deal with sets, unlike when we deal with sequences. Okay, so we will get that this is 0.333, which is decent similarity. Again, it's hard to kind of interpret it in isolation. You will compare it, with similarity of other things. But one thing I want to highlight is, if we go back to our bag of words representation, and if we use, for example, Euclidean distance as a way to measure similarity, we would get that the distance here is 0, therefore similarity is, let's say, 1 minus 0. It's perfect, which would mean that these two things are perfectly similar. So the choice of using Euclidean distance or whatever Euclidean similarity would not be the best choice here, because it wouldn't get us this the fact that these things are not perfectly similar, unlike Jaccard similarity, which gives us that when we use bigrams. And again, it was important to use bigrams, not unigrams, to get this information out. Okay, sorry, I thought someone raised their hand, but now they did.
So is the universe in this scenario everything that we see on the screen here, or is it every possible combination of two words?
Yeah, that's a great question. So here it's not relevant because we're dealing with Jaccard similarity, so we don't need to know that number. What this would be, you would take all the words that exist in all the documents in your corpus and construct all the bigrams from the entirety of the corpus, and that would be your universe. So as many distinct bigrams there are in the entirety of your corpora, that would be that number.
Can you get the property of most of these distance measuring
Sorry, say?
The community property, like what's the outbreak property of not this area?
Gotcha. Yeah, so here we are not talking about distances, and similarity are just, whatever. They don't have the mathematical properties you are talking about. So I don't want to confuse the rest of the students here. We will have a entire lecture dedicated to distances, where we'll enumerate all of the properties that as mathematical distance have to fulfill. And you're right, not every distance will have corresponding similarity. So for example, Hamming distance has corresponding Hamming similarity. So when we have seen Hamming similarity here, we could say there is Hamming distance. That will not always be the case. Yeah. Okay, then for D1 and D3, we get that they are very dissimilar because the similarity is 0. Then D1 and D4 is 1/8, which is smaller than 0.3. And so on. So basically the highest similarity we get here is 0.3, which is intuitive, right? Because we can tell that IM-SEM and SEM-IM are the most similar pairs of documents here. So I think for me, at least, it's way easier to interpret the similarities when I look them with respect to other similarities. If you look at the absolute number, is this high or low? Okay, max is 1. And of course, if you are having 0.9, it's probably close, but it will again depend on application and so on. So I recommend looking at these things in the relative to each other. All right, at least for this example. Okay.
Is it common to use two different K-gram measures and then combine those two to understand the similarity between two sentences?
That's a good question. I have not seen anyone doing that, but I don't see a problem with doing it, right? You can combine all of them. Yeah, I think that's totally reasonable. Yeah, nothing prevents you from doing that. Yeah, there must be some kind of practical issue with it, maybe like probably if you're calculating trigrams, you kind of capture a lot what bigrams are giving you. But I can still see value of understanding, let's say, individual words, unigrams, and then looking at trigrams to make more distinction between the documents. So I think it's a good idea. All right, so we are going to do a little bit of experimental teaching today, and I'm going to ask you to calculate, oh no, not the solution. Calculate the Jaccard similarity for a specific example with specific parameters. However, we are going to use a poll to do that. Okay. All right, so I believe this works like this, but this is me trying it for the first time. You are going to use this link above, and then you will be able to submit your responses. But let me give you this thing again. All right. So this is the thing you need to solve. Read the parameters precisely, and then you will go to this link and submit your answer. And let me know if there are any issues, because as I said, I'm doing this for the first time, so there might be some issues with it. Do you see a link when I do this, or is it now too small? It's over here. Okay. I have too much hope for all of our eyes, I see. Okay, I will do it differently. We'll pull it like this. Oh no. Okay, let's first open the link, and then I will return the actual question. Okay. All right, I feel like this might be okay. This is the link. On the link you submit, and this is the text that gives you instruction. Can everyone see everything they need to see right now? Okay. All right, let's do this. You can put your name or made up name. It doesn't matter. This won't be graded or anything. So yeah, better not put any UIDs just in case someone is scraping this data. Yeah.
Do you consider period as like?
As a yeah, include periods. Yeah, it's written there. Okay, I'm getting a sense that we are finishing this up. Okay. All righty. we have lots of similar answers. Great. Not all of them are the same, right? Okay. All right. Okay. There is some variation here, so let's go over the steps, and I can just hope that I have done it the way you have done it, and that my answer is correct. All righty, so the assignments say what is the value of Jaccard similarity, where we represent the D1 and D2 with character trigrams and include periods. Okay, so all right, I didn't say we should include white spaces here, so we might getting different answers because of that. Here we go. First lesson learned, but if you include white space, these will be your trigrams. So you would have I, white space A, white space M, and so on. So I hope this is clear how you would construct character trigrams. Yep.
Not all characters and or SA.
You are completely right. There is also a mistake here. These are 4 characters, not 3. Great. Okay, so we have that. And then the next step we are going to do is calculate the intersection and union of these 2 collections of sets. Actually 2 sets, which are a collection of items. And we would have that in the intersection, we have all of these. And in the union, we have all of these. So imagine, let's pretend that there isn't a foreground here. And let's see what we will do next in this thing. We would then calculate Jaccard similarity by counting how many items we have in intersection and how many we have in union. Now, I get incorrect answer because there is a mistake here. I have included a foreground, and luckily we will never do this by hand. We will always use Python or whatever you are using to get these kinds of things for us. Yeah.
Well, I'm just thinking about this for like natural languages. This works well for like most, for many Latin-based languages, but I was thinking, what about languages like include characters or really like emotions languages where you make words like by combining many different particles like here or flying away or like.
Yeah. That's a great point, and unfortunately the state of these techniques is such that it's driven by high resource languages, so predominantly English, German, and so on. So like these techniques, when we represent them, they are most studied for English, and I actually don't know how well they would do on specific language you have in mind. And you might be right that there are languages, for example, where one character is way more complex than one character in, English, for example. There's very neat, so maybe you have heard of GPT-3, which is one of these language models that people are using these days, and they have provided a little tool where you can put how much one character is worth. And I have seen someone recently sharing on social media that they put, I don't know which language, but it was character from that language. And then GPT have said, okay, this is way more, their tool has said this is way more costly for training GPT-like model than doing it on English. So yeah, you're completely right that depending on the language you have in mind, this might work not sufficiently well. All right, now I'm really curious what the answer is, but I guess we will use an estimation, and based on the number of times that 3/7 had occurred, say that's the answer. 0. Yeah, this seems like just like I'm just going to put some number. I'm not sure about this. All right, so yeah, maybe I will calculate it and let you know what the correct answer is here. All right, and we have just 2 more minutes, so I want to go back to our roadmap for what we are doing here. And just remind you that now we have done one of the 3 things we need to do we learned about how to represent text with sets. We have learned how to measure the similarity between these sets. Next time, we will going to talk about what happens if these sets are too large, and then we are going to talk about LSH, which gives us the answer to the problem of how to efficiently find similarity of pairs of items. All right, thank you so much.
So that
You didn't want to.
Just a second, just a second. Okay, I need to find okay. Yeah, you got it. Sorry. If I don't turn this off, then you guys are in the